In this example, we want to find the roots of the polynomial x to the fifth plus x to the fourth minus 5x cubed minus x squared plus 8x minus 4. In other words, we want to find the solutions to our polynomial equals 0. To find the rational roots, we can use the rational root theorem. That says if a fraction, p over q, is a root to a polynomial, then the numerator of the fraction p divides the constant term of the polynomial, a naught, and the denominator of the fraction q divides the lead coefficient, an. For our polynomial here, we have that a naught is negative 4, and our lead coefficient, a5, is 1. This means that p divides negative 4, and q divides 1. So the possible values of p that divide negative 4 are plus or minus 1, plus or minus 2, and plus or minus 4, while the possible values of q are just plus or minus 1. Now taking all the combinations of p over q, we get all of the possible rational roots, which are plus or minus 1, plus or minus 2, and plus or minus 4. And remember, we need to evaluate our polynomial p of x at these possible roots and see which ones actually are roots. In particular, we need to find what p of 1, p of negative 1, p of 2, p of negative 2, p of 4, and p of negative 4 are. Evaluating our function, we get that p of 1 is 0, p of negative 1 is negative 8, which is not 0, and that's all we care about. P of 2 is 16, which is not 0, but p of negative 2 is 0. While p of 4 is 972, which is not 0, and p of negative 4 is negative 500, again not 0. So the only solutions we found are x equals 1 and negative 2. But since this is a degree 5 polynomial, we should have 5 solutions. What are the other solutions? Well, since x equals 1 and negative 2 are roots, the factoring theorem tells us that we can rewrite our polynomial as x minus 1 times x plus 2 times some other polynomial q of x. And to find q of x, we need to compute p of x divided by x minus 1 times x plus 2. If you'd like to see the steps of this done out, click the purple link now. Doing polynomial division, we find that our polynomial q of x is x cubed minus 3x plus 2. So we get that if our polynomial is 0, then x minus 1 times x plus 2 times x cubed minus 3x plus 2 has to be 0. And by the zero product property, either x minus 1 is 0, or x plus 2 is 0, or our polynomial q of x is 0. X cubed minus 3x plus 2 is 0. The first two equations lead to the roots that we already found, x equals 1 and negative 2. So how do we solve x cubed minus 3x plus 2 equals 0? We do it the same way we've done our other equations. We use the rational root theorem. Now using the rational root theorem on q of x, we get that the possible p-values are plus or minus 1 or plus or minus 2, while the possible q-values are just plus or minus 1. So the possible roots p over q for our new polynomial are either plus or minus 1 or plus or minus 2. So we need to evaluate q of x at these possible roots to see which ones actually are roots. So evaluating q at 1, negative 1, 2, and negative 2, we find that q of 1 is 0, while q of negative 1 is 4, q of 2 is 4 as well, and q of negative 2 is 0. So we found that x equals 1 and negative 2 are roots of q of x. And these roots, along with the factoring theorem, tell us that q of x can be written as x minus 1 times x plus 2 times some other polynomial. We'll call it m of x. And we can find m of x the same way we found q of x, by dividing our polynomial by our new factors. Here, we need to compute x cubed minus 3x plus 2 divided by x minus 1 times x plus 2. If you'd like to see the steps of this done out, click the purple link now. Computing this with long division, we find that m of x is x minus 1. Now, since x equals 1 and negative 2, the factoring theorem tells us that we can write q of x as x minus 1 times x plus 2 times m of x, which we now know is x minus 1. So q of x is x minus 1 times x plus 2 times x minus 1 again. Bringing this back to our original polynomial p of x, we can now write p of x as x minus 1 times x plus 2 times q of x, which we know is x minus 1 times x plus 2 times x minus 1 again. So we now have a full factorization of our polynomial p of x. And from this, we can get that the roots of p of x are 1 of multiplicity 3, because x minus 1 is a factor 3 times, and negative 2 of multiplicity 2, because x plus 2 is a factor twice.